Have you ever rubbed a balloon on your hair and noticed it sticks to a wall? Or seen how tiny bits of paper get pulled toward a comb after brushing? These effects are because of electric charges. Now imagine this. Instead of a single charge, we place a positive charge, say plus Q, and a negative charge, minus Q, separated by a small fixed distance. That's what we call an electric dipole. This dipole creates an electric field and, more importantly, an electric potential in the space around it. But unlike the potential from a single charge, which depends only on distance, the dipole's potential depends not just on how far you are, but also in which direction you are from it. And here's something fascinating. While electric field is a vector, which means it has direction, the electric potential is a scalar. That means we can add up contributions from multiple charges directly, no need to worry about direction. In this session, we'll learn how to calculate the potential due to a dipole at different positions and uncover some of its unique behaviors. Let's first analyze the axial line, the line that passes through both charges of the dipole. Imagine placing the positive charge plus Q at a distance a from the center and the negative charge minus Q at the same distance a on the opposite side along the x-axis. Now, suppose there's a point P located at a distance r from the dipole's center along the same axis. At point P, the potential due to the positive charge is V plus equals K multiplied by Q divided by open bracket a minus a close bracket. And the potential due to the negative charge is V minus equals minus K multiplied by Q divided by open bracket a plus a close bracket. Here, K is the electrostatic constant equal to 1 divided by 4 pi epsilon naught. Adding both, the net potential becomes V equals KQ multiplied by open bracket 1 over R minus A minus 1 over R plus a close bracket. Now, we simplify this using algebra. And if the distance r is much greater than a, that is, r is much larger than the separation between the charges, then we use an approximation. The result simplifies beautifully to V is approximately equal to 1 divided by 4 pi epsilon naught multiplied by P multiplied by cosine theta all over R squared, where P is the dipole moment defined as Q multiplied by 2a and theta is the angle between the dipole axis and the position vector. This expression tells us that on the axial line, the potential falls off as 1 over R squared faster than a point charge. Let's now move to the equatorial line, that is, a line perpendicular to the dipole axis and passing through its center. Let's place our observation point P somewhere along this line at a distance r from the center. Since the distances from both charges are equal and since one charge is positive and the other negative, their individual potentials cancel out. So what do we get? V equals V plus plus V minus, which becomes plus KQ over R minus KQ over R, which equals 0. Yes. On the equatorial line, the electric potential is exactly 0. This is due to perfect symmetry. The scalar potentials are equal and opposite, and they cancel each other out. But in most real-world cases, your observation point won't be strictly on the axis or on the equator. So what if the point is somewhere else at a distance r from the center and making an angle theta with the dipole axis? In that case, we use the general formula for dipole potential V of r equals 1 divided by 4 pi epsilon naught multiplied by P cosine theta divided by R squared. Let's break this down. V of r is the potential at point r, P is the magnitude of the dipole moment, which is Q times 2a. Cosine theta is the cosine of the angle between the dipole moment vector and the position vector, and r is the distance from the center of the dipole to the point. This formula tells us the potential depends both on angle and distance. When theta is 0 degrees, that is, you're on the axial line, cosine theta is 1, and you get maximum positive or negative potential. But when theta is 90 degrees, on the equatorial line, cosine theta becomes 0, and so does the potential. So the formula naturally captures both special cases. Now let's discuss how this dipole potential behaves. First, unlike a point charge, where the potential falls as 1 over r, here it falls faster, specifically as 1 over r squared. That means, at large distances, the dipole's influence fades more quickly. Second, the sign of the potential depends on the side of the dipole you're on. That's because one side is dominated by the positive charge and the other by the negative charge. Third, the equipotential surfaces, which are the imaginary surfaces where the potential is the same, are not perfect spheres. They bend and curve around the dipole in complex shapes. This is why dipoles are excellent models for molecules, antennas, and even atomic structures. They produce fascinating, non-uniform fields and potentials. Let's solve a numerical example. A dipole has a moment P equals 3 into 10 raised to the power minus 29 coulomb meter. We need to find the potential at a point located 0.1 meters from the center along the axial line. We'll use V equals 1 divided by 4 pi epsilon naught multiplied by P cosine theta divided by r squared. Given P equals 3 into 10 to the power minus 29, r equals 0.1 meters, theta equals 0 degrees, so cosine theta equals 1, and 1 by 4 pi epsilon naught is approximately 9 into 10 to the power 9. Plugging in values, V equals 9 into 10 to the power 9 multiplied by 3 into 10 to the power minus 29 divided by open bracket 0.1 close bracket squared, which is 0.01. That gives us 27 into 10 to the power minus 20 divided by 0.01, which becomes 2.7 into 10 to the power minus 17 volts. So, the potential at that point is 2.7 times 10 to the power minus 17 volts, very small, but significant at atomic scales. Alright, let's recap everything we've learned. An electric dipole consists of two opposite charges placed a small distance apart. It doesn't have net charge, but it does have a dipole moment, denoted by P and defined as Q multiplied by 2A. The electric potential due to a dipole varies with both distance r and angle theta from the dipole axis. On the axial line, the potential is maximum and given by V equals 1 over 4 pi epsilon naught multiplied by P cosine theta divided by r squared. On the equatorial line, the potential is exactly 0 due to cancellation of contributions. And for general points in space, the same formula applies, where cosine theta determines how much influence the dipole has in that direction. The dipole potential falls off quickly, much faster than a single charge, making dipoles perfect models for molecules, dielectrics, and even radio antennas. I hope this has helped you understand how dipoles generate electric potential, even though they carry no net charge. See you in the next session with another beautifully structured concept of physics.